Welcome to note set number 26, where we will be looking at a variety of discrete time system relationships. This is where we'll use the Z transform to really see further insight into how systems behave and how to think about them and how to design them. Although we will be getting more heavily into the design later, the things that we are talking about here are key to our understanding of ability to design these types of systems. So we found the frequency response from the difference equation a couple lectures back, and now we're going to find the transfer function from the difference equation. And don't forget that the frequency response and the transfer function are really closely related to each other. We've already said that the frequency response is the transfer function evaluated on the unit circle of the Z plane, and that should be no surprise, since we saw that the Z transform is really a generalization of the discrete time Fourier transform off from the unit circle. And so here we go. We've got our difference equation as usual. Let me get my pen set up here. And so we've got our output side and our input side with the corresponding coefficients. Now we can do this two ways. Just like we had two ways to do it for the discrete time Fourier transform to find the frequency response, we have two ways here. So we can either consider the input Z to the n, or we can just take the Z transform of the difference equation. So we'll do the second of those things here. So we apply the Z transform to both sides. So here we have the Z transform of the entire left side, Z transform of the entire right side. And so now using linearity, we pass that Z transform through. I skipped a few steps here because it's very similar to what we've seen already with the DTFT, but you should at this point be able to easily follow all these steps on your own. So we take the Z transform. Now the key is when we take a Z transform of something like that, so Z transform of y of n minus 1, by our delay property, we get y of z times z to the minus 1. So that's where we get the z to the minus 1 from this term, all the way down to this term gives us the z to the minus n. And each term has a y of z that ends up getting pulled out in front. So that's what's going on there. And so this is clearly just the delay property in some algebra. And then again, h of z is going to be the thing that multiplies x of z to give us y of z. And so we can easily see here that all we have to do is bring this down into the denominator, and we get some big thing that multiplies x of z. So that big thing is h of z. That's our transfer function. So again, just like for the frequency response, we don't have to do these steps each time. We just did it this first time to see. But once we see it, we go, okay, easy. We take all of our b coefficients from the input side, we put them in the numerator, each with its appropriate z inverse term. We take all of our coefficients from the left-hand side, put those down in the denominator with their corresponding power of z inverse, and we're all set. So by just observation or inspection, we can write this. So now we know how to compute the output. We've got this h of z. We used this filter command before when we were just picking off things from the difference equation or picking off things from the frequency response. Now we can pick things off from h of z. But the important thing is when we have h of z, we'll see in a little while that we sometimes rewrite h of z in terms of z instead of z inverse. It's to get the right form for filter, it's always best to have it in terms of the z inverses. Then we get the right order to put into here and to put into here. So let's talk a little bit further about this and see under what circumstances we convert into the z form versus the z inverse form. So here's the structure that we just saw, and what we're going to do is just simply multiply by some appropriate high enough power of z to clear all these inverses. So when we do that, we end up with a z to the m. We had a z to the minus m here, all the way down to a z to the 0. And then down in the denominator, we end up with a z to the n, all the way down to a z to the 0. Now, depending on the relationship between m and n, if they're equal, we will not have a term that's out here like this. But if they're not equal, we'll have a term that's a z to some power. And if n is greater than m, we'll have z to some positive power out in front. If m is the larger, then we'll have z to the minus power out in front, but we can think of that as being z to the positive power down in the denominator. And we'll do some examples that will illustrate what that all means. Now let's take this numerator and call it b of z. Notice that that's a polynomial in z. We take this denominator, write that as a of z, also a polynomial in z. So these polynomials are going to tell us an awful lot about how the system behaves. So we're going to assume that if there's any common roots between b of z and a of z, that we've canceled those out and redefined new b of z and a of z with those common roots canceled out. So we'll just make the assumption that there's no common roots. So now we define the values, or the concept of poles of h of z. Back when we were doing the residue, we were referring to roots of the denominator as poles, and this is why. So the poles of h of z technically are defined as the values of the z variable on the complex z plane that make the magnitude of h of z go to infinity. So we could analyze this and ask what values make that happen, but it's a lot easier once we get it into this form where we've got a ratio of two polynomials in z rather than things in terms of z inverse, as we'll see in just a little bit. The zeros of h of z are defined as the values of z that make h of z go to 0. So, I mean, this terminology makes sense. Why do we call these poles? Well, it's like a tent pole. A tent pole takes the surface of the tent all the way up, well, not up to infinity, but it does take it up to a pretty high point, and so this is evocative of a tent pole, so that's why we call those poles. Now, to put these in terms of the polynomials b of z and a of z, if we look at the roots of this denominator polynomial, a of z, it's a nth order polynomial. That is the distance between this power and this power. So that's the order of our system, if you remember, when we talked about that before. So we'll have n poles, and then we also have, if we look at the roots of the numerator polynomial, b of z, those are going to give us m zeros. And then we also have to take into account the fact that if m and n are different, there's going to be this term out in front, and we have to account for what that does. So if n is greater than m, then this gives us a z term to a positive power out in front, and that'll give us n minus m zeros that are at the origin of the z plane. But if n is less than m, then we'll end up with this term being effectively a z to a negative power, so we can pull that down into the denominator as a positive power, and then we have a bunch of roots of the denominator at the origin, and those will give us m minus n poles at the origin. So this term out in front gives us either poles or zeros at the origin. And so you have to keep a close eye on that. I've seen some books that don't really pay careful attention to that idea of those poles and zeros at the origin. So let's take a look at finding some poles and zeros for a given system. So here is a difference equation, and we take a look at that and can very quickly by inspection write what the transfer function is. So we get the 2 and the 1 here. The minus 1 gives us the z inverse. Then down below we have a 1, a minus half on z inverse, plus 1/4 on z to the minus 2. So now we have h of z in the z inverse form. And then we multiply top and bottom by z squared. So if we were to take the top times z squared, bottom by z squared, we end up getting this z squared and this z minus 2 to cancel and gives us that. And then finally the z squared times the 1 gives us that. And then up here we have a z squared, 2z squared plus z, and so we can factor out 1z out in front. So now in that case we can take a look at this is our sole terms out in front. That's going to give us a 0 at the origin. This is going to give us a 0 at minus 1/2. And then if we find the roots of this quadratic polynomial, so you should know how to use the quadratic form to determine those, we find that we get a pair of complex poles for that. And notice that the poles always show up as a conjugate pair. That will always happen. So we can plot these poles and zeros on a pole zero plane, or a pole zero plot rather. So this is a plot on the z plane. This is a plot on the z plane. So this is real part of z and the imaginary part of z. So we've got our 1, 0. We use circles to represent zeros and x's to represent poles. And we have a 0 at minus 1/2. So this is the real axis here. And then we have our complex conjugate poles, 1 here and 1 here. Now, we found these things by hand up here, so we could make this pole zero plot by hand, or we can use MATLAB's command zplane. And you can see that for that we should go directly from this. MATLAB's zplane command goes directly from the z inverse form. By hand it makes a lot more sense to convert it into the z form. So we just populate the coefficients, numerator and denominator. So it's a good idea to keep track of these commands and what order you put the numerator and denominator in. I think it's pretty consistent. If we look at this filter command, it's numerator and denominator. Same thing with the z-plane. Okay, so right now we don't really have any idea why we care about these poles and zeros, but by knowing where they are, we'll see in just a little while that it tells us an awful lot about how this system behaves. Let's revisit the impulse response. I think we talked about this before. Certainly for continuous time system, we're going to hit this system with a delta of n and see what comes out. And why we do this is not necessarily clear at first, but it'll be clear that this is actually very much related to the frequency response as well as the transfer function. So we'll tie all these ends up later on, but for right now let's just talk about hitting the system with a delta function and seeing what we get. So we put in this delta and out comes something. If the system is causal, it'll be 0 all the way up until the earliest point n equal to 0. We can see that the z transform of delta of n is equal to 1. So using the property of the transfer function, we can find that the z inverse of h of n is just as usual. This is just an input, so we're going to take its z transform times h of z, take the inverse z transform to get the thing that's the output. We just use the symbol h of n to represent the impulse response. But since this is 1, all we have left in there is h of z. So what we're seeing here is that this thing called the impulse response is nothing more than the inverse z transform of our transfer function. And similarly, the inverse dTft of the frequency response is the impulse response. That makes complete sense because the z transform and the dTft are very similar to each other. So this is a nice little insight. It tells us that h of n and h of z form a z transform pair. So now we can start getting some insight about these poles. So when we have an h of z that looks like this, if we do a partial fraction expansion on that, we're going to get things broken down into all the factors of a of z. And if we assume we don't have any repeated roots and we don't have any direct terms and things like that, then what ends up happening is for each of the roots, each of the poles, we'll get a term that looks sort of like that. And so we've made some simplifying assumptions here just to be able to illustrate some points easily. But this is a very key idea, and we want this impulse response to decay. If the impulse response grows without bound, then we would have a system that's not very usable. And so in order to do that, we need all of these p sub 1s and p sub 2s, the poles, to have magnitudes less than 1, because otherwise we're raising them to powers, and if they're bigger than 1, they're going to keep growing bigger and bigger and bigger. So what that tells us then leads us to this concept of stability. So we define a system to be stable if its output will never grow without bound for some bounded input signal, whenever any bounded input signal is applied. And that seems like a good thing to desire of our system. So we could go into a lot more details. I'm kind of waving my hands over this a little bit, but the basic idea that you need to know is that a system is stable whenever the poles are inside the unit circle. The zeros can be anywhere. So here's an example of a pole zero plot that shows a system that is stable. All the poles are inside the unit circle. We've got a couple zeros outside the unit circle, but the zeros can be anywhere. Also notice that everything that's complex shows up as conjugate pairs, so that they're a mirror image around the real axis. So when we're designing a system, we want to make sure that it's stable. Otherwise, we could put in some signal and the output would grow without bound, and that would not be desirable. It'd be like that bridge that you've seen the video of, that with just a little bit of cars driving across it and some wind blowing, its response grew without bound, and it ultimately broke into pieces and spew the cars and people onto the to their deaths, I guess. So we don't want that. So now let's revisit this relationship between the transfer function and the frequency response. We've already said that the DTFT and the Z transform are related by evaluating the Z transform on the unit circle. Now that's only valid if the unit circle is inside the region of convergence. Now for all causal systems, we can show that the unit circle is inside the region of convergence if all the poles are inside the unit circle. So that means causal, stable systems, we can evaluate, we can convert the transfer function into the frequency response. So since causal systems are what we're interested in, stable systems are what we're interested in, that means that if we have the transfer function of such a system, we can easily convert it into the frequency response. And all we have to do is evaluate the transfer function on the unit circle. So there's a command in MATLAB that allows us to, from the frequency response, be able to get the transfer function, and this command is called Freq. We've already seen this before, where we filled in these quantities based upon the difference equation. Well, those coefficients reside here as well. So we look at the Z inverse form of our transfer function, pick off the coefficients as appropriate, fill them in here, pick some appropriate range and grid spacing for our omega, fill that in here, and go ahead and compute and plot the frequency response. So now let's visualize this relationship between the transfer function and the frequency response. So here's a transfer function. I've written it in terms of Z, and I've already factored the denominator into two complex poles, two factors with complex poles. So we've got a 0 at the origin, and we've got our complex conjugate poles accordingly. And so there's a pole 0 diagram for this. We've got the 0 at the origin, and then we've got a pole, two poles, 0.8 in radius from the origin, and at plus or minus 0.3 pi. So we go up 0.3 pi and out 0.8, and there's one pole, down 0.3 pi, out 0.8, and there's our other pole. So there's our pole 0 diagram for this particular system. And we can imagine these poles taking the Z transform, the H of Z, up to infinity at those points. That's exactly what those poles do. Now, we can think about walking around the unit circle, and we can think about starting over here at minus pi and walking around the unit circle and ending at pi. So we would be starting over here at minus pi. So this is the real axis, this is the imaginary axis. Didn't really draw that very well, but here's 0, so the imaginary axis kind of goes through there, or that's the real axis. The imaginary axis kind of goes across there. So we start over here. We're starting here. That's starting right here, and we're going to walk around the unit circle. And as we do, the values on the magnitude of the H of Z follow this curve, and I'm kind of going around the poles there. And so that's how we visualize. And what this is telling us is that we can look at the pole 0 plot, and when we see poles that are close to the unit circle, that means we're going to be walking close to a pole, and that's going to drag this tent surface up. And so that's going to cause the frequency response to have a little bump there. Now we don't have any zeros that are close to the unit circle, but if we were to run across a zero, it would tack the tent surface right down to the ground. So this gives us a great way to visualize. And so to then turn this into the kind of plot that we're used to seeing for the frequency response, what I've done is created a plot here that shows that curve. So if we go back here, so this little curve here, I'm just showing that kind of cookie cutter cut out. So here it is, real z, imaginary z, and then here's what we're going to do. We're going to imagine cutting right there. That's at the minus pi point. So that's minus pi. We're going to cut right there. And then we're going to unwrap it. So it's sort of like, you've gone to Burger King. You've got the Burger King crown that you got. They give it to you lying flat, and you have to put it together to put it on your head. We're doing the opposite. We're taking the Burger King crown, taking it apart, and unfolding it. So this part becomes this. This part over here becomes this. And these peaks here show up here. Now I'm plotting this omega over pi, so that's why it goes from -1 to 1. So we're really plotting omega from minus pi to pi. And so we can see that when we get near the angle where we encounter those poles, we have spikes. Now it's not exact, just because of the way that it pulls the surface up, but we're going to have a peak in the vicinity of the angle where the pole exists. And we also have this idea that the closer the pole is to the unit circle, the more pronounced this spike is going to be. In this case, we had poles that were at 0.8. That's pretty close to the unit circle. If those poles were at 0.2 away from the origin, then we would not be seeing such pronounced peaks. Now the cool thing is you can experiment with this, right? You can go back to something like this, and you can by hand select these values, smash that back together into a polynomial, convert it back into z inverse form, and then use Freq Z to make a plot of your frequency response. So you can kind of play around with trying to guess, okay, if I put a pole here, what's this thing going to look like? And then you can also play around with the numerator and put different zeros in. You can put a 0 here, maybe put a 0 here and here, and play around to see what those things do. So that's good practice to learn how to visualize that. Okay, so let's continue on with this idea of being able to visualize the effects of poles and zeros on the frequency response. So this pole zero placement is a really good way of thinking about the system, and without the Z transform we would never have this insight of these poles and zeros. But a lot of filter design and system design comes down to fussing over where these poles and zeros are. And these pictures are from one of my favorite books, Signal Processing and Linear Systems by B.P. Lathy. Excellent book. You may be wondering why I don't use it. It's really thick, and it doesn't quite cover the material in a fast enough way to be able to cover it in one semester. So anyway, we're looking at these pictures here. We've got a bunch of different pole zero plots. So here we've got a pole near the origin at 0, and we're only plotting 0 to pi because everything is symmetric. But when we have a pole at 0, we're getting something spiking up there. And if we add a 0 at the origin, notice that nothing happens to the magnitude response, but the phase response does change. So a zero or a pole at the origin does nothing to change the magnitude response. Now if we place a zero over here, now that's going to affect at minus pi and pi. So the distinction we see is without that zero, we didn't go all the way down to completely attenuating to zero, but now we do. So it's helping us convert this into a better low-pass filter. And if we want to continue this idea and put this even further, we can now kind of populate a few poles around zero, and that's allowing us to flatten this out more and push it out to make a nicer pass band. And then we put a whole bunch of zeros. So when we show some concentric circles there, we're showing a multiple of zeros. It looks like there's maybe 3 zeros there. It's common to write the number of them next to it, but this book didn't do that. So what that does is these poles kind of flatten this out, and we've got multiple zeros pulling this down and making a better low-pass filter. Now if we want to make a reasonably good high-pass filter, well, now we put the zeros there. That's an angle of 0. So we're starting off at omega equal to 0, and as we walk around this unit circle from here, first we encounter the 0, so we start at 0, we walk around like this, and we start encountering poles, and so that makes us go up. But these things are kind of structured there in just the right way to make it kind of level off flat. So that's a nice way of thinking about this. So you should practice this, and you can always check it out with Freq. Now let's talk about a cascade of systems here. Suppose we have a cascade of 2 systems with frequency response and transfer function, frequency response and transfer function. It's pretty easy to show just by taking the output of one and putting it in as the input to the other one, that the result of a cascade of systems is just that the total frequency response or total transfer function is just the product of their individual ones. And this can be carried out to however many. If we have n systems in cascade, it just becomes the product of them all. So we'll stop this here.